Yeah, thanks so much for having me here. It's really great to be back in Heidelberg, and in particular to see more of the Heidelberg AI community. Because when I was studying here, I was mostly exposed to the natural language side of things. Yeah, natural language is still mostly what I'll be talking to you tonight. And in particular, I'll be talking about transfer learning, and mainly one aspect of transfer learning I'm particularly excited about and I think is particularly important, which is transfer learning across different languages. So typically from English to any other language that you care about. And in this context, I find it useful to motivate why we would actually want to do transfer learning, or particularly cross-lingual learning, why it makes sense empirically, why our machine learning methods should actually be able to yield some improvements on this. And generally, for transfer learning, I've observed that it's most useful when the tasks you're trying to transfer between share some underlying similarities, whether using different features or relying on different underlying structure. And for similar reasons, also transfer learning across languages can be useful, because also languages, if you ask linguists, share a lot of underlying structure on different levels of meaning, both from the word level, from different grammars that are shared common across different languages, as well as on higher semantic levels of meaning. And in this context, transfer learning is particularly useful when the annotated, the labeled data you have for the task or the setting you care about is expensive to obtain and very limited in practice. And in this case here, for many languages in the world, many languages only have a few speakers, or few speakers that are available on crowdsourcing services that we would usually use to gather annotated data. So in practice, transfer learning really here is useful to transfer to languages where we simply do not have the resources available in practice. And kind of maybe as a last reason, empirically we've seen for transfer learning for English, we've seen successes and state-of-the-art results across a wide range of different common tasks in natural language processing. Just to show one particular example out of kind of the variety of successes here, I'd like to show here named entity recognition, which basically aims at identifying an entity, so a mention of typically a name, an organization, or whatever other category is relevant for the particular task, with its corresponding type. So in Wikipedia, for instance, you would want to tag Barack Obama with the type person. So this is kind of a classic sequence labeling problems, and people have been working on that on this particular standard benchmark all the way starting in 2003. And what is nice about this, looking at progress here on this task compared to more recent tasks where we've only seen kind of the last years of progress, is that most of the kind of larger bumps in performance on this graph can be seen as being due to different forms of transfer learning, of using unlabeled data to yield improvements for this particular task. And in the beginning, these were in particular approaches that leveraged better word representations based on some unsupervised clustering based on large unlabeled corpora. And more recently, kind of the last sequence of bumps here were based on different variants of models that were based on deep pre-trained neural networks, which are now pretty much common in most areas of natural language processing. And another commonality that we can see here is that over the kind of early years in this task, a lot of progress was made by just improving representations on the word level, whereas most of the later improvements have been due to deep representations. So representations that go beyond the word level to the sentence or document level. And also, kind of a similar trend I hope to show you today as well, for representations across different languages. And now I've just used transfer learning so far kind of as a general term here. And transfer learning has a long history as well, and has been used in kind of all kinds of different areas, not only in NLP, but in most of the other areas in machine learning as well. And so just to put what I'm going to be presenting to you here in a bit more context, I'd like to think of transfer learning across kind of different dimensions in terms of the current approaches that are mostly used in NLP these days. And in particular, I think the main settings we can differentiate by are whether the source and the target setting between which we're transferring information between, whether they're dealing with the same or different tasks. If we're dealing with the same task, then typically we either transferring between different domains, so say between news corpora, which are very common in NLP, and Twitter corpus, or a corpus that is maybe has biomedical information. Or, and this is what I'll be mainly talking about tonight, whether we transfer between different languages, so between English and Spanish. And then the other setting that is very common these days as well is a setting where we transfer between different tasks. And in that case, I think the most differentiating factor is whether we have access to the training data of all of those tasks at the same time. So in that case, people typically train one joint model via multitask learning on those different tasks, or what is now very much common these days is that you have one task that is typically some surrogate task that you actually do not care about, but which you can use to learn good representations from large amounts of unlabeled corpora, and then using the pre-trained model from that task, you then apply it to some other target task. And I'll be kind of referencing these models, but I'll be mainly spending time on cross-lingual transfer learning here. Now, I've kind of made before the point that why cross-lingual learning intuitively should make sense, or why it might be useful in practice to share features or to transfer information across different languages. But I think there's also a very good reason kind of from a societal point of view to make for why we should not only work in English, but on other languages, and should leverage information we have in English to do better in those other languages. And in particular, I think in particular one observation that we can make is that the language one speaks really shapes what types of information we have access to, what information we're able to consume online, and also what types of people or connections we have access to. And kind of thinking that further as ML and NLP technologies become more pervasive, the language will also kind of determine and play a very big role in what types of technology you have access to. So already these days we can see that maybe only English speakers have access to the latest features of Google Search or Google Assistant. And as these assistive technologies become more pervasive, we need to make sure that we actually have a level playing field, and that not one particular population or one particular number of speakers is predominantly advantaged by our technologies. And as one particular motivational example, we can look at a say we're in New York here, and we want to use kind of a popular maps application to look for a dining location. We can enter our query in English, and we are presented with a number of options here, which maybe reflect our tastes. We can do the same thing in another widely spoken language. In this case, we get kind of a similar set of options with some notable differences. If you can see that here, some of the restaurants we present here are more on the kind of Latin American, Spanish side of flavors. And lastly, if we now make this query in kind of another language, which is spoken by a few number of speakers, we now not presented with any option at all. And this is just really only the tip of the iceberg. A lot of the failures, a lot of the problems we might encounter are not as obvious as like complete lack of results, but might be a lot more subtle, and could also be in the form of biases or just not having very good performance on these models, as we've already kind of seen examples in other domains, like in facial recognition systems, for instance, as well. Now, on that note, I've already mentioned, and throughout the rest of the talk, I'll be kind of talking about like high resource and low resource languages. And typically, I'm going to use that. I think in NLP, people typically use that to talk about the number of resources, the number of data that is available for a given language. And even though there's not kind of a clear distinction between them, but like we all know that machine learning models are very data hungry, so the amount of resources we have available for each language directly determines how good of a model we're able to train for those languages. And in NLP in particular, the main sorts of data we can differentiate really by are firstly just number of documents or the number of text documents we have available online, so simply on the web, whether a language is really represented on the entire web or in common kind of web-based corpora like Common Crawl. And depending on how many documents they actually have available there. Secondly, of course, only a few languages have actually access to large label data sets in practice. And another common data source in NLP is Wikipedia. So also languages with very large Wikipedias are also easier to work with in practice. And then if we kind of go down the pyramid for languages where we do not have any of these data sources, so for which there is barely any data on the web, or there are only small Wikipedias available, these languages kind of historically have really been under-researched. So in general, typical most of NLP's research has really focused only on the tip of this pyramid, of this iceberg, while really kind of most of the more than 6,000 languages that are spoken around the world are really a lot harder to work with if you have models that require learning from large amounts of data. And I think this is also one of the motivations for this research direction, that we really would like to find better ways to serve the rest of this pyramid. And the solution for that I'm going to try to advocate for throughout this talk is based on learning representations. And you can see that mainly in contrast to classic methods in NLP, because pre-deep learning, pre-neural networks, typically the common way to solve a problem or to apply methods to another language was to compute or to generate language-specific features that would represent kind of the linguistic intuitions in that language, and to perform language-specific pre-processing as well. And typically that would then allow you to kind of train language-specific models. Whereas these days, kind of more increasingly with deep neural networks, the kind of alternative approach is to learn cross-lingual representations as well. So to learn representations that somehow represent the meaning in different languages in the same embedding space, and then use those for transfer, kind of using this general transfer learning formula that has already been successful in the monolingual setting. And here, kind of just as a disclaimer, I mean, I'm mentioning that kind of previously language-specific models were most frequent, but there's already been a lot of research on cross-lingual transfer, like pre-neural networks as well, and there's kind of alternative ways to do this sort of cross-lingual transfer rather than just learning representations, with the main difference being here that these sort of cross-lingual representations that these models are trying to learn are generally kind of thought to be general purpose, so that they're not geared to one particular task, but can be applied to many different downstream tasks. And now this the transferring formula that I just touched upon already, and that has been kind of successfully applied to achieve state-of-the-art performance across a wide range of different NLP tasks, really just consists of two steps. So given a large amount of unlabeled data in your language, you would use your pre-training method of choice. So pre kind of deep representations, people used word2vec and GloF, and now more recently models such as Elmo and BERT have been more common. And then using that method, you would learn some representations. And now the only thing you would need is some amount of labeled data in your target task. And you would typically fine-tune or use your representations that you learned as features to kind of transfer that knowledge to your new task. And the main difference now in the cross-lingual setting is that we just kind of add an additional step in the end. So also here in this case, what I'm mainly going to be discussing in this talk is this initial step of how we can actually learn these cross-lingual representations in the first place. And kind of the important part of these representations is that they really put words or sentences or higher level semantic units that have the same meaning across different languages as close to each other as possible in this embedding space. And then, given that we have learned these cross-lingual parameters, we can then, given label data in our target task, learn some amount of task-specific parameters on top of them. And now, kind of the general assumption is that given that our initial parameters that we use as features are already cross-lingual, the parameters that we learn on top of them should also be cross-lingual enough. So they should not really represent any knowledge in any of the particular languages, but should mostly represent knowledge that is particular to the task, which can then work with any of the other languages. And then, given this fine-tuning stage, which is typically done in the data where, in the language where the most amount of data is available, which is typically English, we can then freeze our cross-lingual parameters, typically here, and apply our model just via zero-shot transfer. So by now using instead of an English sentence, a Spanish sentence, for instance, and applying that directly to the target language. And if our model in the beginning was able to learn some cross-lingual alignment or some embedding space that captures the similarities across different languages, we would expect in practice for it to also do well when zero-shot transferring to another language. And as I'll kind of show throughout the talk, in practice that depends on some settings, but works surprisingly well in others. These representations naturally can be learned on different levels, from the word level to deeper representations on the sentence level and beyond, which is kind of what I'm mainly going to be talking about through this talk. So in the beginning, I'm just going to highlight and focus on representations on the sentence, on the word level, both how we can use supervision and to learn these, and then going on to methods that learn these representations without any supervision at all. So without anyone telling the model, okay, these two words mean the same thing in different languages. And then from then on, we'll look for similar types of unsupervised methods, but for learning deep contextual representations. And I'm going to add on some open problems and directions. So for the first part here, there's been kind of a large history of models that try to learn this sort of cross-lingual embedding space on a word level. Also preceding neural networks and preceding word-to-vec even. So before that, people used just SVD and other ways to construct distributional vectors of words. And also since then, there's been kind of a variety of different approaches. And the main approach that I'll be describing here is now the most commonly used one, and it's most popular mainly because of its simplicity. Because in practice, this approach really, the only requirement is that you have pre-trained word embeddings in your source language, such as English here, and your target language, such as German. And you can obtain these pre-trained word embeddings just by using your favorite word embedding method of choice, like word-to-vec. For instance, training those word embeddings separately on their respective monolingual corpora. And then the only thing we're trying to do here in these mapping-based approaches is to try to find an alignment, so just a linear transformation matrix that allows us to kind of rotate and convert the embedding space of the source language here, so that words and their translations align in this projected embedding space. So that this kind of projected embedding space is as close as possible to the original target embedding space. And kind of as you would assume, or the first method that proposed a way to solve the solution really did this in perhaps the most obvious way as well, by casting this as an optimization problem and just trying to minimize the square distance between this projected embedding space. So here our source word embedding space transformed with our linear transformation matrix with the original target embedding space, given some number of C translation pairs in both languages. And then given those translation pairs, we can then iteratively, by just applying SGD to that, try to find matrix W in such a way so that it brings the projected embedding space and the target embedding space as close together as possible. And just to provide a bit more intuition how this might look like geometrically, here we basically start out with our source embedding space and our target embedding space, where each word is represented as a point in the overall embedding space. And now what we're essentially just trying to do is to find an alignment, so some way in which we can rotate and scale our source embedding space so that words in their translations here, so here between English and Swahili, are as close together as possible by minimizing our optimization objective. And these translation pairs, or the words where we try to minimize the distance between those, we require to be provided in advance. So here we require someone to tell us, or someone to give us a list of words and their corresponding translations. This was kind of the first approach, which, given its simplicity, worked actually surprisingly well for the language pairs that it was evaluated on, such as English and Spanish, for instance. And from then on, this kind of spawned and sparked off different approaches that tried different variants, different ways in which to change and improve possibly this objective. So there's been kind of a lot of different variations of that, and probably the most enduring modifications of these was to constrain this transformation matrix that we're trying to learn to be orthogonal. And the main intuition why orthogonality should help is that if we have an orthogonal matrix and we transform the embedding space, then we kind of constrain it so that the relations between the words that we have in our source embedding space are still being preserved in our target language embedding space as well. And that then helps, particularly because in the end, what we want to do well on is not just the words that we have in our initial translation list, but all of the words in our vocabulary, which are typically on the order of 200,000. So we want our transformation to be as kind of generalizable in general as possible, and the orthogonality constraint really helps with that. And the second nice thing, which people only kind of realized later on, was that if you require this matrix to be orthogonal, then instead of having to do SGD, this can actually just be solved using linear algebra. So this is just kind of a classic problem known as Procrustes problem in linear algebra, and the solution to that, so the transformation matrix W here, is then really can just be calculated using singular value decomposition. And the kind of interesting thing here is that even though this linear transformation and this orthogonal transformation is kind of very easy and can be implemented in one line of code, basically, this is still being done and is still one of the same part in all mapping-based approaches, even ones that have been proposed in the last year. So even though they're kind of adding a lot of other bells and whistles and a lot of other improvements, this initial mapping-based approach is still staying the same. And you might wonder, okay, have people tried different ways to obtain this mapping? People naturally in the deep learning era tried deep neural networks as well, but in general people have really found that the transformation that is kind of generalizes the best to your vocabulary is like the simplest one as possible. So it's just this constrained linear transformation, which seems to work quite well. And now I just mentioned here some bells and whistles, and one kind of additional component that has been quite successfully used, and that is particularly useful when you only have a very small translation dictionary in the beginning, is what people refer to as self-learning. So instead of only doing this sort of transformation once and then being done with it, you can use the transformation to when you project your source embedding space to the target language, that gives you kind of some nearest neighbor candidates, which, given that you've learned hopefully good transformation, should likely be translations of each other. And now, using those nearest neighbor candidates, and maybe including your previous dictionary, you can get a new, larger dictionary that you can then again use for seed for learning a new transformation. And people have observed that if you iterate that a couple of times, you can get even better results. And in practice, like this additional kind of self-learning loop has allowed people to achieve good results kind of from the beginning, where people relied on like around 5,000 translation pairs. With this one, you can get good results with about 25 translation pairs, and which are really like a lot more common and a lot easier to obtain in practice than having to ask for 5,000 translations. And now the other interesting bit is that the main difference between supervised and unsupervised approaches is not in this mapping nor in the rest of the self-learning. So it really consists just in the initial step how we obtain the initial seed dictionary. So for supervised methods, we obtain the seed dictionary from some linguistic resource or from some supervised data that we have access to. And now the crux for these unsupervised approaches is to generate an initial seed dictionary. So as we know, this can be small, it can also be somewhat noisy, but at least it should be somewhat useful, it should contain some signal enough to learn something from that. So how can we generate this in a completely unsupervised way? And one common approach, also as we expect, there's been different approaches for this. Some casting it as an optimal transport problem, so trying to minimize the distance between the two distributions. And one common approach, or one of the earliest ones that I particularly want to highlight here, is based on learning this in a kind of sort of adversarial setup. And this adversarial setup might sound familiar to you if you're familiar with generative adversarial networks. So it's kind of based on the similar components in like a slightly different setting over here. So the main setting is again similar to the GAN setup. We also have a generator and a discriminator here. Now the generator's job is not to come up or to imagine a totally new image or a totally new word. No, the generator is here parameterized by our transformation matrix W. And the generator, given a word embedding from the source language, then basically just aims to transform this embedding into kind of a fake projected embedding. But by doing so, trying to fool the discriminator that this projected embedding actually comes from the true target language distribution. So that this embedding is actually kind of indistinguishable from words that actually come from our target language embedding space that we try to align to. And this seems maybe a bit challenging in practice. So the main underlying intuition here, why this actually should work in practice, is that because we know from GANs, in order to kind of consistently fool the discriminator, the generator actually needs to, as best as possible, be able to match the distribution of the source data with the data it generates from. And the main kind of now hypothesis why we would want to apply this method here is that the best way to align these different embedding spaces with each other, the best way to minimize the distance between the two distributions, is also the way that puts the translations of the source and the target language embedding space close to each other. And now, kind of already before, you might have picked up on that, but even more so here, really, in order to be able to find this possible alignment or some way to minimize the distribution between these differences, we really kind of rely on the underlying assumption that our word embeddings in the source and the target language have a similar underlying structure, so that we can actually minimize the distributions in some meaningful way. And to again go back to our initial example of the two distributions here. So in the supervised setting, we know about the identity of all of the words that we're trying to align to each other. In the unsupervised setting, we basically are only left with 2 point clouds. So we only have access to the embeddings, the points in each of the 2 embedding spaces. And now the hope is essentially that our generator, by kind of consistently trying to generate and project these sorts of embeddings into the target language embedding space and trying to optimize that objective, that it will be able to find over time a better and better alignment, and in the end, that alignment that minimizes the distance between the two distributions also puts the words or the points that it puts those together would correspond to translations as well. And now, just so this was kind of more like conceptual here, and just for a bit more kind of the mathematical details, just very quickly, as we've seen before, the generator here is just a linear transformation matrix, as we had before, and the discriminator is just another neural network that just gets its input, either the projected embeddings or the target samples. And in typical GAN fashion, basically, we have two losses that we try to optimize alternatingly. We have one loss for the discriminator, which basically for both the projected embeddings and the original target embeddings, we try to classify them correctly so that these are incorrect and these are correct. And for the discriminator here, we basically just have the other portion of the loss where we try to maximize the probability of classifying them incorrectly. And and people have just, with similar tricks as in typical GAN training, tried to optimize these successively using stochastic gradient descent to some success. Now I've just to kind of give you some numbers, actually be able to show you how well these methods do, or what you can actually do with these methods. I'm going to show some performance on one particular task that is people like to use in this setting, mainly because it's very easy to evaluate on this task, because it's almost because it only acts on the cross-lingual word embedding space itself. And the task here is, people call that bilingual lexicon induction, and it's mainly just about finding the word translations using your cross-lingual word embedding space. So given a kind of a gold standard list of words and their translations, you take the original source word, look it up in the embedding space, and then check if its closest nearest neighbor is the corresponding translation. And people typically evaluate that on accuracy, so whether it gets the correct translation right or wrong. And in some early papers that propose these approaches, we've kind of seen numbers that were on the line of these. So these are accuracy numbers. So generally, kind of for a lot of languages, or particularly, so these are basically kind of mapping, typically in all cases, from English to corresponding target language. So in this case, it's English to Spanish, each way kind of the other way around as well, English to French, English to German, to Russian, to Chinese, and to Esperanto, kind of an official language. And kind of interestingly here, we can make a couple of observations. First, we see that for some languages we actually get quite high performance. So for like English, Spanish, and English French, we get performance more higher than 80%. So 80% of cases the model is correctly able to identify the translation. And secondly, we can also observe that here, in this case, actually the unsupervised approach outperforms the supervised approach in quite a few settings, which is surprising given that the supervised approach actually has access to strictly more data in practice and strictly more information. Another interesting or another important point why this is relevant to talk about is that here, for this setting, in contrast to kind of most typical settings for machine learning, it's actually fairly easy to get enough supervision to actually train these supervised models. So as I mentioned before, we can train these supervised models with as little as 25 translation pairs. And because there's a large amount of linguistic resources online, such as Wiktionary and other kind of small databases, and a lot of those already give you a small number of translation pairs for a lot of the world's languages. So these unsupervised approaches are really kind of only justified empirically or in practice, other than kind of theoretically interesting, if they are all able to outperform the supervised approaches consistently. And another thing that we can also observe, like from a linguistic standpoint, is that many of these languages that are being used here are not actually that different linguistically. So they are not actually using. So most of the initial ones are Indo-European here, and otherwise we do not have any agglutinative languages or any ones which might be morphologically very, very challenging. So now if we actually look kind of at a more representative evaluation and compare this same unsupervised approach from before to a supervised approach on kind of a wider set of languages. So these are now again English to Spanish, this is English to Estonian, to Finnish, to Greek, and then Hungarian, Polish, Turkish, and Estonian to Finnish in the end. So if we look at kind of a wider set of languages, we can really see that the unsupervised approach actually for a few of those language pairs fails completely to give any non-zero performance. And the main reason, or this is kind of weird given that like kind of previously we've seen it's generally very competitive in most settings. And the main explanation why that is lies really in this underlying this initial unsupervised alignment step that we use initially to obtain our initial Z dictionary. And in particular, as I mentioned before, kind of the underlying assumption of this step for the embedding spaces to be similar. Because in practice, and as I'm going to show now, the embedding spaces between words in different languages are actually not all that similar, depending on your measure of similarity, and that this really influences the performance of this unsupervised embedding approach. So now, how do we actually want to characterize this similarity of the embedding spaces? And one kind of obvious way might be, given that we already have our word embeddings and we are looking for nearest neighbors anyways in the graphs, we can just characterize the similarity based on whether these whether the graphs in these embedding spaces have similar structure overall, similar connectivity patterns. So in general, whether they're kind of approximately isomorphic. And if we study that for not only similar but also dissimilar languages, we find that this kind of assumption of approximate isomorphism that most of these unsupervised approaches kind of make under the hood actually does not strictly hold even for very related languages. And for more dissimilar ones, this actually holds to a far lesser degree. Now, just to make that a bit more concrete, we proposed here one particular measure for that can be used to characterize this discrepancy between the embedding space structures. We basically just looked at the eigenvalues of the Laplacian matrices of each of those two graphs, which kind of represent some of the kind of connectivity patterns of each of the graphs. And then if we just look at the top k eigenvalues of those two graphs, the top 2k eigenvalues of both graphs, and take the difference between them and sum that up, this sum of the differences, if that is very large, we would expect the embedding space to be similar, and for the same to be dissimilar. And if the graphs were very similar, we would expect a small difference overall. And now, if we kind of plot this dissimilarity actually against the performance that I mentioned before, we can see kind of very strong or clear correlation overall in that languages which achieve the highest performance have a low difference of eigenvalues, whereas languages that achieve comparatively low or even zero performance on the speaking and lexicon reduction task achieve a far higher, have a lot more different eigenvalues here. And since we proposed this initial metric, there's actually been kind of a couple of other metrics that have been proposed based on different other attributes of not only the graphs but also of the structure of the overall networks. And all of them kind of show a similar or even higher correlation with the performance of these types of methods. So we can generally see that this is really an underlying pattern, that these methods are quite sensitive to the underlying structure of these embedding spaces. And if we plot that again here, we can see English, Spanish, and the other things on the other side here. And now just a few takeaways from the first part of the talk here regarding unsupervised representations on the word level. As we've seen and as subsequent studies showed as well, at least the current set of methods are not really competitive with their supervised counterparts, at least if we actually level the playing field. So if we apply all of the bells and whistles and the improvements we've made to our unsupervised methods, also to our supervised methods, which a lot of the early papers actually did not do in practice. Yeah. So in some cases, the playing fields have not been level really. Then, as I showed you, still these unsupervised approaches really fail, particularly for the more distant language pairs. And as we've seen in some more recent studies as well, actually the main challenge here is not directly overcoming typological or linguistic similarities or differences between the languages, but a big source of these similar structures in the embedding spaces is the amount of data that they've been trained on. So we can see that word embeddings, so the initial monolingual embeddings for a lot of these low resource languages, just not a lot of data, or typically because they're trained on Wikipedia, the Wikipedias are a lot smaller compared to high resource languages. So the embeddings are also going to be of poorer quality, and consequently also going to be harder to align to more high quality English embeddings. So generally, I think a good avenue for improving these approaches is actually making sure that we train them on sufficient data in order to have high enough or high quality enough representations. Then for supervised representations, one thing that I didn't mention explicitly here, but for instead of just getting a small number of translation pairs, another kind of interesting approach is to use weak supervision based on the similarity of the scripts of the different languages. So one thing people tried and actually works surprisingly well in practice is that in order to use gold translations, you can use more noisy initial translations by assuming that all words that are spelled the same in different languages also have the same meaning. So while in general this will give you some like false friends and some words that do not really correspond to each other, on the whole, a lot of the words will be numbers or named entities which do in fact mean the same across different languages. So even if you do not actually have gold translation pairs, you can still, simply using this very simple heuristic, get good and performance supervised models. And lastly, because supervision is that easy to obtain, it's often preferable in practice if you want to apply these methods to your task of interest. And just if you really want to get out there and get your hands dirty, the most robust baselines that we've identified are really these two, VecMap for unsupervised mapping and kind of an extension of this supervised approach, of the kind of typical supervised approach that we proposed here. And for now, because I've only talked about one particular type of supervised method and one particular type of unsupervised method, if you are very interested in this topic and you want to get a broader overview, we've also done a tutorial at NACL on that gives you kind of a wider overview of some of these unsupervised methods. Cool. And so now these were, the talk so far was on representations just on the word level, where we try to learn some sort of cross-lingual embedding space that brings words and their translations close to each other. Now the remainder of the talk is going to be about learning such representations, but at a deeper level. So now using kind of more state-of-the-art deep contextual representations in NLP. And if you talk about contextual representations these days in NLP, one thing that you can't get around is BERT. Yeah? So if you haven't heard of BERT yet, it's basically an acronym for bidirectional embeddings from transformers. And it's essentially just a big transformer model that was pre-trained on a large amounts of unlabeled data. The main kind of parts of the model are not really relevant for our task here. The main thing that I want to draw attention to is that BERT has stack of multiple transformer layers here, and the main thing that is of interest for this talk is that the representations that it has for each word, or in this case for each subword, because BERT also uses a joint subword vocabulary that, based on some frequency information, sometimes splits up some longer words into more or less meaningful chunks. For each word, we have kind of a separate token embedding, which might be more similar to your classical word embedding. We, in addition, have a position embedding that, given because an attention model is kind of does not pay attention or cannot take into consideration the position of the word, allows the model to learn kind of a feature representation where the word occurs in the sentence. And then we, in addition, have a segment embedding that, because this model can also be applied to tasks that take pairs of sentences as inputs, allows the model to basically have different embeddings for the first and the second sentence. And then in practice, this model is typically pre-trained what is known as masked language modeling, in that a proportion of words in the input are masked randomly, and the model is then tasked with predicting the corresponding words, so basically just filling in the blanks, being able to impute the data here. And this model is trained on for a long time on lots of text online. And after this pre-training phase has really been shown to learn very useful representations, that then, if you simply apply this model to a downstream task, like here, for instance, what is known as natural language inference. So given a premise and a hypothesis, we want to predict in what kind of logical representation they stand to each other. So whether they contain, whether one entails the other, whether one contradicts each other, or whether they are neutral towards each other. And if we fine-tune the model for the task, we can get very, or at least on common data sets, we can get very good performance in these cases. Now, this was now solely applied or generally applied in the monolingual setting, typically in English as well. And however, in applying this model in the cross-lingual setting is actually not that difficult. The main, it's actually very, very simple, and the main change that we need to do is now, instead of training that on only data of one particular language, we combine our corpora in multiple languages, and instead of learning one vocabulary per language or just one vocabulary, we learn a shared subword vocabulary where we share kind of all of the tokens in all of the languages in the same vocabulary. And kind of the main side effect of that is that now in this shared vocabulary, words or subwords that are spelled the same in different languages now get assigned the same embedding and have the same ID and the same embedding here. Yeah. So the model is kind of incentivized to, or basically gets forced to represent them in the same way if they're spelled the same across different languages. And now with this model, we pre-train it just the same as in the monolingual setting, again using masked language modeling, now just kind of alternating between batches of different languages that we feed into our model. And now, again, for fine-tuning, similarly to what we've seen in the beginning of the talk, for generally applying a cross-lingual model to another task, we can now fine-tune this model, which, as I'm going to show you, or as has been shown, surprisingly is able to learn like useful cross-lingual representations in its body. We can now, given it's learned these cross-lingual representations, apply it to label data in another task where we only have the label data available in English, fine-tune it on that data. So again here on natural language inference. And now apply it via zero transfer to the same task in our other language, and kind of expect to do reasonably well on that again. And maybe this might seem surprising to you, or surprising that this actually works at all. Like to me, I think it did as well, because this model, kind of in contrast to the supervised methods that we've seen earlier, and also in contrast to these unsupervised methods, is actually throughout its objective not really forced at all to find any useful alignment between the different languages. So for the unsupervised approaches, we've at least had some term that tries to minimize and bring the distributions together. This model does not have that at all. It's simply trained on data in different languages, but somehow is able to find or learn representations that still represent meaning or shared meaning in the different languages in similar locations in the same space. Kind of alternatively, like another kind of hypothesis, if we hadn't seen the performance of these models, might have been that maybe the model would just be able to learn or be able to figure out to partition its embedding spaces into separate languages and just reserve different parts of its embedding space for different languages. But in practice, it seems to do more than that. And there's been a couple of studies analyzing the behavior and really trying to probe, okay, why is it working that well, which have brought forth a couple of different hypotheses. With the main ones being that the shared subwords that I mentioned before, that having these same embedding and the same IDs for similarly spelled words in different languages serves kind of as anchoring the model for those languages. So similarly to these to the weak supervision that I mentioned before, where we have also the same we assume words that are spelled the same in different languages to be translations of each other. Here again, the model, starting from this initial supposedly quite good alignment, might be able to kind of distribute and find a way to align the surrounding words of the remainder of the words in the vocabulary as well. And then kind of another ingredient, of course, is in order to be able to kind of learn this alignment, the model has to be jointly trained, so it has to see examples from both languages at the same time. And people have really kind of observed or hypothesized that this alignment, the representations that this model is able to learn, actually go beyond just doing a superficial alignment on the word level, but actually the model is really able to learn some deeper cross-lingual representations. And now what I'm going to show you with an example or kind of an alternate counterpoint approach, so to say here, is that these three things are actually not relevant at all for learning cross-lingual embedding space, and in turn kind of make us question really what these models learn in the first place, and also the kind of the usefulness or maybe the importance of knowledge that is captured in monolingual representations by themselves. So the approach I'm mentioning here basically just does without all of those 3 points. So instead of learning model jointly across different languages with the same vocabulary, we will start out with an English model with different vocabulary compared to the other language, and only afterwards kind of learn new representations in the other language. And while this might sound complicated, it's actually fairly simple the way we are using it here. So the initial phase is basically just as you would pre-train your regular bird model, in that we would have our bird model which we pre-train again using masked language modeling in our source language such as English here. And now in this case the only kind of change, the only difference that we're bringing into in the second phase is to keep all of the parameters of our model fixed. Yeah? So all of the most of the parameters of our bird model from the English bird model are getting frozen, and we now only learn new token level embeddings for the new vocabulary in our target language. Again, using masked language modeling here on the embedding space of our target language, only updating here the new the token level embeddings from the target language, and hoping that they kind of align or fit into our existing English parameters. And now again, similar as before, we can now fine-tune this English model, and kind of if you would previously think or be of the opinion that in order to be able to learn useful cross-lingual representations, you actually need a joint vocabulary or you need to do joint training, then you basically would here expect that because we only align like these token level representations there, that the model would actually not be able to learn anything meaningful at all. But in practice, and as I'm going to be showing you in a minute, just doing this very simple like lexical level alignment is actually able to find a very good cross-lingual alignment between the two languages as well. And given now that we've learned kind of some cross-lingual parameters in our model, we can now again do the same transfer setup as before, where we can just fine-tune our model in on the label data of the task in English, with the only change that we really want to maintain our alignment with the embeddings from the other language. So we update all of the parameters except from our English token embeddings. And we now just, in the zero-shot transfer phase, basically apply the same model as before to the target language, just swapping into our embeddings from the target language and hoping that they kind of are aligned to the remainder of the model. Now for the actual results of the experiments, we're applying that in the same setup as before. In this case, we're just learning representations on Wikipedia, fine-tune the model on label data of the target task, and then apply that to the test data in the other languages. And the data sets that we are working on are kind of some commonly used cross-lingual data sets in NLP. The main ones that I'm going to be showing you here are natural language inference. So this is basically the task I already used as an example, and a new data set that we've gathered based on translating existing question answering data set. Also fairly typical task in NLP these days. And just the comparison methods that we're going to be comparing to here is just this multilingual word model that I mentioned before, as well as a more recent approach that basically takes the same setup, same architecture, but scales it up and trains it on more data. Because we want to really isolate the kind of the impact of doing this joint training, we look at training both a joint model across all of the languages we have in our task, as well as training models just pairwise on only the source and the target language. And we also isolate for just having a disjoint vocabulary in this joint training setup as well. And then finally, we also compare to the methods I mentioned in the first stage of the talk, in particular to like the best cross-lingual word embedding method that I recommended to you previously. And we propose kind of different variants of this monolingual transfer setup. So just our regular setup where we just learn these token embeddings. And then, because different languages have different word orders, different grammatical structures, so it might be useful, in addition, if you remember, we have not only our token embeddings, but our position embeddings as well. So it might be useful not only to just learn the token embeddings, but also the position embeddings for another language. And similarly, because the main kind of the critical point here is that doing fine-tuning, our model has not worked with or has not seen the actual embeddings in the target language. So we want these embeddings, when we plug them in the end, we want the model to be as robust as possible to like some variations in those. So we also propose to add some additional Gaussian noise to those embeddings to just make the model more robust overall. And then finally, because the one main disadvantage of this method here is that really all of the parameters, in order to maintain the alignment, all of the parameters of the model are being kept frozen. So in order to still introduce some additional flexibility, we propose to use something that is called adapters. So those come originally from computer vision and have been recently used to do more parameter-driven fine-tuning. And these are simply kind of small transformation layers that are typically plugged between the kind of larger layers in your neural network and allow you to keep the main body of your network frozen while learning kind of a smaller number of task-specific parameters for your particular task. And typically this allows you to fine-tune your model without having to fine-tune all of the parameters of the model. And in our case, the intuition would be that these would allow us to learn some language-specific functions that are useful for that task, while still keeping kind of the main copy of our model intact. And now here for natural language inference, as I mentioned, the task is basically given a premise and a hypothesis. We want to classify the relationship between them. So here, between them here, the relationship is entailment. And the data set that is commonly used for this in cross-lingual setting was basically generated by translating an existing monolingual data set, by translating kind of the test set of that into 14 other languages. Now for the results, we can both first see here that XLM, so this kind of more recent model, outperforms our original multilingual BERT type model. We can also see that here our cross-lingual word embeddings, actually, if we kind of make sure that they're of the same dimensionality as our other embeddings, are kind of achieve somewhat similar performance on English, but actually do somewhat worse on the transfer, particularly when it comes to transferring to some of the low-resource languages like Swahili here. We can then see that for joint learning, actually learning a model across all of the 15 languages actually hurts performance. And in particular, the model that uses a disjoint vocabulary does actually better than a model that shares the vocabulary across different languages. So that actually shows that we don't really need at all, even without this monolingual transfer setting, having a joint vocabulary between different languages. And as we later show with some additional ablation studies, the main kind of point of importance is not here how many languages you're using, but actually how much vocabulary you have available per language. So here in this setting, because we have a disjoint vocabulary, we have two vocabularies of the same size with a smaller joint vocabulary, so a model is also able to get better performance. And now, in comparison to that, our monolingual transfer setting with the original, kind of with the plain vanilla setup, just learning the token embeddings, achieves performance that is somewhat competitive, but slightly lower compared to the jointly trained models. But then, if we also learn the position embeddings from scratch and add some additional noise, we are able to basically be competitive or almost, perform slightly lower compared to the best pairwise approach here. So really, kind of this approach, which is only really learns a very superficial lexical alignment under the hood, is able to be competitive compared to these kind of what we thought to be approaches that learn kind of more meaningful or deeper cross-lingual representations. And then for the second data set, this is based on question answering, where you might have heard of the Stanford question answering dataset, which is kind of one of the most widely used benchmarks in NLP these days. And because of that, similarly as before, we basically took that benchmark, the subsets of the development data of that benchmark, and also translate that using professional translators into a number of different languages, so that we can evaluate models' cross-lingual transfer performance. But again, same caveat as before, because it's translation language has kind of its own properties and its own characteristics, and while being useful for measuring, may kind of still overestimate models' true underlying generalization performance. Now, for performance of this task, we can actually observe that here on this more challenging, more complex question answering data set, cross-lingual word embeddings actually perform a lot worse. Yeah? So they were pretty good at classification before, but for something more complex like this span extraction for question answering, they're not able to kind of express as much knowledge here. And then again, for the joint learning, we see the same pattern as before, in that the joint vocabulary is actually not useful, even with larger differences in between. And here, now for the monolingual transfer model, we can see now actually that adding position embeddings and noising actually hurts performance. And this might be in this case because span extraction really, the way this task is framed, typically requires the model to be able to point to the beginning and the end of the span in the corresponding document. Yeah? So it doesn't generate the answer, it just points to where it thinks the answer is in the paragraph. And for this pointing, the model needs somewhat accurate representation of position in the input document. And if we learn these position embeddings from scratch, the position embeddings might be useful for the target language, but might not be that useful for the actual task where they are being used for, which might explain the drop in performance here. And finally, we can see here now that if we add adapters, these kind of give the model this additional flexibility that we wanted for it to be very competitive with the actual with the performance of the jointly learned models on this task. Cool. So now just for the final takeaways here. So we've seen from these ablations and the different analyses that actually for learning these cross-lingual representations, we actually do not need a joined subword vocabulary. And also, as was kind of previously thought or has been hypothesized a lot, training on more languages directly, if you don't adjust your vocabulary, actually does not help, but can in fact hurt performance. And in practice, what we've identified is that keeping the remaining parameters of your model the same, or even if you proportionally increase other parameters of your model by making it deeper or wider, the most important aspect in this setting is really just an effective vocabulary size you have per language. So how many tokens or subwords in that language are represented in your joined vocabulary, or the one that you're using. And secondly, regarding the monolingual transfer, we've really seen that even this, what I think it looks like to be a very superficial form of transfer, in that we only really learn new word level representations for our new target language. That actually performs surprisingly well. It's even competitive to these approaches that we thought learn very deep, or representations that go beyond the single lexical alignment. So on the one hand, there's kind of questions really what these jointly trained state-of-the-art approaches like multilingual BERT actually learning in practice, if the same results can be achieved by this by just learning new tokens embeddings for your target language. And secondly, I think it also highlights that monolingual representation itself maybe capture more knowledge that might be cross-lingually relevant than we previously thought. So they might be more useful for, so instead of training models from scratch for other languages, might be actually more effective in practice to find some way to transfer from a very good English model in the first place, even though it is in another language. And secondly, in general, we've observed that cross-lingual word embeddings actually were only competitive on the very simplest tasks that we looked at, so for cross-lingual document classification, and performed more poorly on the other ones. However, that doesn't mean that they shouldn't be used in practice. So for they're a lot more parameter efficient and more efficient at inference time, and serve kind of very well simpler use cases like just doing cross-lingual document classification. Cool. And now I just have a couple more open directions here, and some maybe additional talking points. And I think generally one highlight here, or one kind of running thread that ran through the talk, was generally how we evaluate these models, and that we should be more careful about evaluation. And in the past, also people have found different issues for the way these cross-lingual word embeddings are evaluated, in particular with the commonly used data sets for this particular task. And people have also found issues with just using this task as a proxy for the performance, because while it is very easy and very simple to evaluate on the task, what we actually care about with these models is that they do well on any downstream task that we want to apply them on. So in the end, we do not want to end up with models that might be interesting or doing well at word level translation if they're not useful for anything else. And as we kind of saw in some of the experiments, that some existing tasks are actually too simple, such as cross-lingual document classification, actually maybe too simple to get an appropriate picture which method is better than each other one. So in general, we need to have more challenging benchmarks for, particularly for cross-lingual applications that really challenge these cross-lingual models and really allow us to better ascertain whether they're actually learning anything useful or just purely lexical alignment. And then on the same note, I think there still needs to be more work on actually understanding where this non-isomorphism comes from. So as I briefly alluded to, we've done some experiments, and it seems that the amount of data plays a big role, but also it's necessary to look more in what role typological differences, so kind of the linguistics, play actually in the nature of these different embedding spaces. And secondly, in terms of these deep representations, given that our models maybe do not actually learn as much as we thought they would, how can we incentivize actually kind of more deeper multilingual understanding in these models. And for that, I think we still need better ways in order to probe and really get at what these models are learning at their core. And finally, given that a lot of the content in this talk was really motivated from some like big societal problems, or actually some practical applications, maybe the zero-shot transfer setting that we're studying here is kind of useful in general and kind of appealing because we do not actually need any label data. But in many cases, or in many document applications, having access to large amounts of label data in English or another high resource language might not be feasible either. So in practice, actually just being able to make better use of like a small amount of label data in your target language is really quite a worthwhile direction as well. And at the same time, given that we want to apply these models to actual real-world applications, actually dealing with the resource constraints and being able to make our huge models more efficient is an important research avenue in itself. And with that, there's a couple of references regarding to papers I mentioned throughout the talk. And yeah, besides that, I really want to thank you for all your attention and for sticking around so long. And yeah, thank you so much. And I guess we have some time for questions.
Would there be hope to do embeddings that can generalize across language families? So German has enough literature to have a decent embedding, as we saw, and maybe there's less for Swedish and Norwegian and Icelandic. So.
Yeah, that's a great idea. So there's actually, I mean, I've only touched on some of the literature here. There's quite some recent approaches that, I mean, typically one other disadvantage of some of the methods I talked about, was that they assumed in every case we want to transfer from English. That's actually like generally not the best choice. So often if we have access to some data from a member of the same language family, like German and English or other languages.
Finnish and Estonian.
Yeah, exactly. So if you remember that particular graph there, going along the way back. So yeah, basically in short, it's often a better choice to transfer from a different language. So here, whereas we get, for the unsupervised approach, 0 performance here, if we choose a more similar language for doing this alignment, we actually are able to achieve some performance. And yeah, in practice, there's been some interesting recent studies on that. And interestingly, often choosing even kind of the language you would perceive as most similar based on like linguistic differences is actually empirically often not the best one. So there's so people have basically also proposed ways in order to learn which way or which multiple languages potentially are the best languages to transfer from.
Thank you for the great talk. One question: you showed that if you use disjoint corpora in a multilingual setting, that it's better. And also you showed that we can fine-tune this multilingual model on only just, let's say, on English. Does this fine-tuning have to be in the same domain? So is it possible to fine-tune or train multilingual model to a completely different domain with maybe with words that were never seen before? Do you have experience on that?
So I actually haven't looked at that in practice. The main reason being that there's not that many like cross-lingual corpora available to actually evaluate these. I think in practice, if it's like a somewhat similar domain like Wikipedia or News, you would probably still be able to do somewhat well. Whereas Wikipedia does some biomedical documents might probably not work at all. So I think I would expect the performance to be similar to things that people have observed for machine translation, for instance. So for machine translation, people have also seen that if you have your machine translation model and you that is typically learn news, and then you want to translate data in like a very different setting or a very different domain, that typically does a lot worse.
So what score would you require for the whole thing to be useful?
Well, I mean that depends on the needs of your particular application that you're working with, I guess, and on the how much of a critical business application that is. Whether 1% error rate is enough, or whether you can work with 10% and get some user feedback in loop. I guess in general. I mean, so this is kind of one disadvantage of these zero-shot models is that you get overall some good performance, but I think in order to use them in actual business applications, you probably still, I mean, until at least we're the same performance in English, you probably still want to go out there and at least get some additional label data, because label data, if you can get it in those languages, does not hurt. But these approaches might be useful. In the beginning to bootstrap that, or to apply it to completely languages where it's very hard to get the data source. Okay. Yeah.
Sorry. Maybe I can ask another question. So not super familiar with the field. How does that work on different modalities? I mean, I know there's stuff like transcription. Can you, in general, combine different representations of language? Or, for example, if you work with audio, is that a completely different architecture or model you use?
I mean, so recently the trend seems to be going that to use a transformer or bird-like architecture for no matter the modality, right? There's been recent models that are basically take the same setup like BERT but apply it to vision and language tasks, for instance, treating vision kind of as another thing you can predict, and learning a joint embedding space between different languages in more or less unsupervised way, as long as you have examples of vision and the corresponding language, so based on a large captioning data set, for instance. So as long as you have, I mean, adding the other language dimension obviously complicates that, but it would. I can't think if multimodal works separately and this works separately. I can't think of a reason why adding the additional modality wouldn't work otherwise, other than probably requiring a lot more data and requiring to train the model longer. Cool. I think probably everyone is getting hungry for pizza. So yeah, we can have other questions up later as well.